Hello, everyone, and welcome to this new EPET module. Today, we'll be talking about onboard computers. So this is module 9. We'll be diving into what it takes to not just design an onboard computer, but also how to use an onboard computer in space and some of the mitigation for some of the hazards that you will find in space. I hope that you will, at the end of this lecture, will be able to understand what it takes to build a computer for your particular mission. And let's dive into it. So some of the overview topics that we're covering today, we'll be covering the onboard design, onboard computer design. We'll be talking about some of the primary functions, also an example of some of the space-grade computers that are available today, in the form factor for computers, especially for CubeSats that we'll be especially focused on. Then we'll be talking about the onboard computer hardware, the main features, some state-of-the-art computer examples that are out there, rad-hard computers, rad-tolerant computers, what's the difference between them, and then an example for a payload computer. Finally, well, not finally, but continuing with onboard computer electronic components, especially the memory and some of the electrical interfaces that are found in some of these computers. And then we'll be talking about some radiation effects and how to mitigate those effects. And then we'll be talking again about our mission and how the onboard computer for our mission can help us have a successful mission. And this is the example of the PyCube and the Billabong boards that are the main elements for our onboard computer. Okay, so diving into the onboard computer design. We have, since the 60s, right, we have developed several flight computers, and there is now a science behind how to build space computers. And some of these main functions that we need to be considering when developing these computers and using them is to make sure that they're useful, of course, for the main aspects of our mission. So it's always important to relate back to the requirements and understand how the requirements really help us to identify what the primary computer should be for our mission. But here's some of the common functions that our computers will do, flight computers will do. So uplink command reception. So you want to be able to send a command to your spacecraft, execute that command successfully, and then possibly transmit some data back to the ground station. So you want to validate those commands, process, distribute those commands. Sometimes that data has to be shared to other computers in the spacecraft or other subsystems. And then you may also want to store the data. So the computer has to do these functions. The computer also needs to manage the state of health, SOH. We abbreviate it many times by this acronym. And then we want to format that state of health message and also store it. When we say format, is basically say what goes in which order in terms of bits, bytes, and maybe even the message sequence. Then we have, sometimes we need to handle data rate for the payload or high throughputs. And if you have a camera or some other high throughput device or sensor, it's important to know how capable your computer is to process that incoming data. And again, formatting that data and store it for later downloads. And then we also want to make sure that the computer can, if necessary, process data in real time. Because sometimes you want to query your spacecraft about a specific subsystem or state, and you don't want to wait for an orbit or 10 orbits to get that data. You want to be able to get it immediately. On the right side, we have an example of the CubeSat ISIS space computer, which we are actually using for one of our missions, the high time mission at HSFL. So let's look into some of the general purpose functions that flight computers should have as well. There's an executive control. This executive control usually is implemented in software, and today we have enough capability on flight computers to be able to do this in software, usually implemented in C, C++. Maybe we're looking into Python to be able to do some of that, but typically it's implemented in the traditional programming languages. We do have other aspects like timekeeping. So a computer needs to timekeep, so you know not only where your satellite is, but also to tag the information as it's been stored. So that information, time tag that information. And then, of course, like I mentioned before, the command and script execution, health monitoring. So we want to be able to monitor not only how the CPU is behaving, but the memory and other aspects of your computer. So there's a watchdog usually implemented with this. You want to also make sure that your computer is safe and secure. So if people might try to hack your computer from the ground, sending RF signals, if it's easy to access, your data, your mission may be compromised. And then sometimes this is optional, but the flight computer will also execute mission planning and operation functions, so that if you have to somehow let the computer decide what is the next step on your mission, you need to implement some of that logic. And there we enter some of the intelligence and autonomy that spacecraft computers can implement nowadays. And then, like I mentioned before, a little bit to the payload control and data processing are also optional. Many times we use two different computers, one for the primary functions, which we call the command and data handling, and then the payload computer just dedicated to the payload to acquire all the data in real time and store it. And then the flight computer will talk to the payload computer and exchange the information as necessary to download to the ground. On the right side, I have an image of a typical flight computer overview and some of the elements that to make the flight computer. So you can see there's a microcontroller in the middle. That microcontroller is where the main software resides. And then there's a A to D, or analog to digital converter. You have a transceiver interface here, so a CAN interface. So this is basically to connect to another sensor or memory or some other third-party device. And then you have RAM and flash, so memory types that communicate with the microcontroller and store the data. To run an operating system or the various state of health messages and things like that. So if you are more interested about this particular design, you can click on this link. So why can't we just use a regular computer in space? And this is something that I think it's important to clarify, because, why can't I just, put my iPhone computer and have it my main processor? There's several reasons for that, and I'm going to try to emphasize one particular reason why we cannot just use any regular computer. So here are three examples, three stories that demonstrate that. In 2013, there was this player playing Super Mario 64, and suddenly he jumped to another level. Like literally the height of Super Mario was upgraded to another level, and nobody really knew what happened. And by the way, this was streamed on Twitch, so that's why we have record of this event. And only several years later, about 8 years later, is that someone found out that there was a bit flip in the height section of the memory for this particular game, and that bit flip allowed you to jump to the next level. So it was a mystery for many years, but eventually it was found out that there was just this little glitch that made the jump. In 2008, this was a much more serious event. An Airbus 330 was en route to Australia and suddenly pitched down, and several people were injured. In fact, it was not just once, but twice that this happened. And they came to, the investigators came to understand that this was a single event upset that had caused, again, a bit flip on the spacecraft, on the flight computer for the, not the spacecraft, in this case, the airplane computer, to create a glitch that made the computer confused about what kind of information it was collecting. And there were no safeguards against this type of confusion, and the computer just decided to dive, and that was very dramatic. Fortunately, no one died, but it hurt seriously at least 12 people. And then another example happened in 2003 in Germany, in Belgium, where a voting machine during some elections increased the number of votes for a particular political candidate, Maria Vindevogel, and added 4,096 votes. And this was mathematically impossible because she did not even have that many number of known people that were going to vote for her. So they went back, and fortunately they had recorded the votes on magnetic cards, and they found out that that had been a glitch. 4,096 is actually a number that is an exponent of 2 to the power of 13, because, and that was another reason why it was easier to identify what was the glitch, because that bit flip had basically added this number of votes. So this happens in space. This is all caused because of cosmic radiation and other radiation effects in space. So if we can observe these types of events here on the ground, not often, but they do happen, they're much more observable in space. So these 3 stories are all related to cosmic radiation effects. These usually are ionizing particles from outer space that can change the transistor states from a 0 to a 1, or vice versa, a 1 to a 0. So this is the source and the origin of this bit flipping. But so this is one of the primary concerns. But there's other concerns that we also consider for flight computers. So others are power limitations. We don't have much energy in a small volume when we deploy these little CubeSats. We have mass limitations, volume limitations. So all of these are critical. But of course, radiation effects are the damaging effects that we so much want to avoid. Wanted to show you all also how the computer evolution has happened, or the space computer's evolution has happened compared to the typical computer on the ground, like, you know, our Pentiums, and Pentiums were quite old already, but so there's this Moore's law that shows how many transistors can fit into a particular die of a computer. And so we have evolved the computer capability over the years according to this Moore's law. The space computer is also moving along that law approximately. But the problem is that it's about 10 years behind. So the computers that you see now in spacecraft are quite old compared to the capability that we have on the ground here. Now, these curves might actually be coming closer a little bit together, but still, it is the flight computer industry is very conservative because, again, we want to test these computers extensively and make sure that they are capable for operating in space. You don't want to jeopardize a $1 million mission or $100 million mission just because you're putting the newest and shiniest computer in your spacecraft. So there's a lot of rigorous testing that goes on for these space computers. So the problem is that you don't have as much throughput or processor capability, and that's usually measured in million of instructions per second, MIPS. But many times we optimize the code and we optimize the functions on the spacecraft to be able to fit in. So this gap here is important for you to remember. Don't expect the shiniest and greatest flight computer out there. Very well. So let's talk a little bit about the OBC form factor for the onboard computers. A standard that has been adopted is the PC-104. And this is an industrial standard, not necessarily a spacecraft standard, but many CubeSats have adopted this standard because of its compact form, but also plug and play capabilities. So this fits within a 10 by 10 centimeter volume, which is, again, the CubeSat form. It's been used by several industry or space companies like ISIS-Space, Clyde Space, ComSpace. Here at HSFL, we also have developed our own flight computer based on this form. And if the standard PC-104 dimensions, which is these, so 3.7 by 3.5 inches, if this is not enough to plug in or install all your components, vendors are also adding these mezzanine boards or daughter boards to their interior space on the PC-104 so that you can add more functionality. We're using something like this for the high-tech CubeSats. And here's an example of how stackable these boards can be. So very, very stackable. So this form factor also means that there is a connector, a standard connector that interconnects these boards. So you don't have to worry too much about if I plug these two boards together, are they conflicting in terms of power or data? And so for the CubeSats, we have developed these CubeSat key bus connector over the years within the community to standardize what we mean by the power and the data for these connectors, so that if you buy a board from another vendor, in principle, it should match your connector. But due diligence is important, so you always have to check and work with the vendor to make sure that you are getting the right interfaces. But here's some typical examples. So you have two header pins. So these two connectors here are 52 pins each. So header 1 and header 2. And inside of that header, you have a standard power bank. And usually you find the ground, the 5 volts, the 3.3 volts, and VBAT. VBAT means the battery voltage, which can be unregulated. So sometimes it can be 7 volts, 14 volts, 16 volts, depending on your battery configuration. And then you have the standard interfaces. So I2C of the system, I2C internal, UARTs, etc. Okay, so let's talk a little bit more about onboard computer hardware and the various solutions that are out there. So one thing we want about an onboard computer is to have it highly integrated. We don't want too many boards laying around and things like that, especially for CubeSats. We want it to be modular and reusable for multiple missions. We want to be able to combine multiple microcontrollers, FPGA, CPUs, memory. So again, we don't want things laying all over the place. We want to use standards, so we don't have to redevelop the wheel every time, a new standard every time for electrical interfaces, for software interfaces, for mechanical interfaces, and things like that. And more recently, field programmable gate arrays, or FPGAs, have become quite common in flight computers because they allow us to actually program the logic or the hardware logic into that FPGA, meaning that you can implement different transistor circuitry, different electrical interfaces, even implement different hardware CPU implementations. So that is very important, becoming more and more important today. Also, CubeSats are typically designed around COTS, or customer off-the-shelf parts, because these COTS basically lower the cost of a part dramatically. These are COTS usually is, you buy a microcontroller that Texas Instrument develops, and there's thousands of them available. It used to happen that many flight computers were developed using non-COTS parts, so basically everything from scratch, and of course that becomes extremely expensive to develop. But the advantage of that would be that you could design exactly how protected your hardware is from radiation, and you have increased reliability. But COTS have been catching up in terms of reliability for space computers. In fact, some companies like Microchip, they give you options for space-rated microcontrollers, transistors, and other devices like that. So this is just an example of the space shuttle computer. You can see it was a bulky computer, modular possibly, but it still used a lot of volume to feed every function of it. Of course, the space shuttle is a very different flying machine than our CubeSat, but this shows that typically this is how flight computers have been developed, and now we're moving towards a more compact shape and form. Here's some of the state-of-the-art computers that exist today for CubeSats, but also small satellites. And I'll just mention a few and walk you through these tables. So here's the manufacturer column. You have the product model. So if you go to their website, you can actually find these models in there. And then you have the processor column. So this allows you to see what kind of processor. In this case, it's a Texas Instrument MSP 430. You have a Xilinx ARM Cortex A53. So Xilinx usually is known for their FPGAs, and now they implement CPUs as well into their FPGAs. And then here's the pedigree. So what kind of availability is there. So if it's COTS, that means it's typically easily available. The manufacturers produce a lot of them. Here's with some mitigation effects for radiation. This one is red hard, which means it's hard to get any better than that. In fact, this RAD 750 is one of the mainly used flight computers for critical missions. So the Mars missions and things like that, they use the RAD 750. And then what kind of vehicle you can use for these kinds of computers. So CubeSat type or general satellites. And then here's the technology readiness level. That means the higher the number, up to 9, the more higher quality that computer is, meaning it's been also in space several times, not just being developed in the lab. So TRL 5 or 6 means, okay, here's a computer being developed in the lab, it functions, but now we want to move it to space. And once you have exercised that computer several times in space, it becomes TRL 9. So that means if you choose a TRL 9 computer, you are guaranteed that that computer will function in space. I'll maybe mention one more. There's this computer here sold by Moog, but in Europe, it's sold by Unibap. And we have working extensively with Unibap on this flight computer for the payload, the high-tie payload. And it's a rad hard, or actually rad tolerant by design, and it can be used for many types of satellites. I'll have a few more slides about this later on. Okay, now we have some examples here of radiation hardened processors. These are the types of processors that if you buy one of them, you're probably going to spend $1 million, but then you're guaranteed to have a reliable mission. So these Virago computers, COBAM computers, this BAE 5545. So these are new and modern computers that are coming out there that are rad hard. And then Xilinx and Microchip have also developed these FPGA type computers. So this Microchip Polar Fire is a good example. Many missions use that one, and etc. There is this number here that I'd like you guys to start to understand. 100 kilorad total ionizing dose means that this is the dose, radiation dose that you can accumulate over time. And 100 kilorad is for maybe a 4 to 5 mission, so 4 to 5 year mission in low Earth orbit. Very reliable. Most typical CubeSat parts you will see out there, they're within the 20 to 30 kilorad range. And I'll be talking a little bit more about this later on. Okay, so let's talk a little bit about more practical examples. Here at HSFL, we have developed a radiation tolerant computer. It's called the HSFL OBC, or onboard computer. And we have currently version 3.3 is flying on Neutron 1, the Neutron 1 CubeSat mission. Our current version is now at version 3.5. And here's a couple pictures of the computer. We use the Yocto Linux distribution. So we basically, Yocto is a tool or framework that allows you to build Linux from scratch. And then for flight software, we're using the Cosmos Core libraries. And then in terms of hardware, so we conform to the PC104 standard. We have the Gumstick Lovera Ironstorm COM. This is the little processor board that is in the middle here. It's like a mezzanine board. And then this uses an ARM Cortex A8 processor running at around 800 megahertz to 1 gigahertz. It has Wi-Fi, which is useful for development, but we don't use that for flights. And then the processor is this DaVinci DM3730. These Gumsticks boards are coming out of stock. And so we're actually considering now a different configuration for these, or a different CPU for these boards. And just to mention, this is useful. This computer is capable of about 2000 MIPS, or Droystone MIPS. This is the measure of how capable the computer is. So millions of instructions per second. This is how you can compare 5 computers quite reasonably well. And it uses about 2.5 watts of power. So it's not insignificant, but it's also not extremely high for CubeSats. Typical CubeSats nowadays use between 1 and 3 watts of computer power. Okay, so here's another example. So this is the ISOSpace OBC. This is also a TRL-9 flight computer, and it runs at a lower speed than ours. It's at around 400 megahertz, and they use different operating systems. Typically, they use FreeRTOS, which is a real-time operating system, but it's capable of multitasking. And then they also use Kubos, Linux. The onboard telemetry provides voltages, power control, and real-time clock. So again, the typical functions that you expect from a flight computer. And these are all just features that are listed for this computer. One other thing that I wanted to mention is that this computer uses 32 megs of SD RAM and also 1 megabyte of NOR flash. You will see later on why I mentioned this, but these are typical radiation tolerant memories that we can use for flight computers. Okay, and now we jump into the PyCubed, which is one of the boards in the flight computer we're using for our mission. So this is an onboard computer with 32 bits ARM M4 processor, or microprocessor, I should say, running at around 120 megahertz. And there's a bit of a difference between microcontrollers, microprocessors, and processors. So microcontrollers will typically run around hundreds of megahertz to maybe, dozens of megahertz to maybe 100 or 200 megahertz. Then the microprocessors will be around 100 to 500 megahertz, and then processors will be 500, 600 megahertz up to several gigahertz, like 1 or 2 gigahertz. So the more gigahertz, the more power you're going to be using, but also the faster the computer is in running your instructions. So it depends on your application. The PyCubed is an open source, so that's one reason why we're interested in it. It's been radiation tested, and it includes several functions into this little board. So the ADCS, telemetry and control, EPS, or power system. So these functions are all condensed into a single board, which saves a lot of space for our CubeSats. This here is the radio. So even the radio is condensed here, which is great. This board has been tested on the KickSat-2 mission previously, and so there is some reliability and some known factor that this will work in space. So here's some of the main interfaces and functions. There's the command and control of the spacecraft, CNDH. We have the energy harvesting and power management. There's the telecommunications. data collection and storage, payload interfacing, and fail-safe deployment mechanisms. Here's a block diagram of how everything is connected. So you have the microprocessor here in the middle, the M4, and then you have the analog signals going on to the right, and for the power banks, and then the burn wires. You have these digital signals. You have an external Watchdog timer. You have the communication section also running via UART. UART is a type of serial communication protocol. And then you have the payloads here that can run via the SPI. So it's good to start to learn about these different interface capabilities, because this is jargon that's usually common for flight computers. And if you want to connect another payload or another power bank or something like that, you will have to learn about what's the right interface to do that. And here's an overview of the different functions of the PyCube. Again, here's the microcontroller right in the middle, the LoRa radio, which actually can be not just LoRa, but FSK. We have implemented FSK modulation in this radio, which we will be using. Here's some of the payload board connectors. So some of these are not populated, depending again on the mission and the capabilities. The battery input, the voltage regulators, the IMU, the inertial measurement unit, the RAM, MRAM is magnetic RAM. And so you have all of these different functions that allow you to functionally create a flight computer that can collect all the telemetry necessary for the mission, store it, and then redistribute it via the radio. Okay, and I'll jump on to another kind of computer for just as an example. This is a completely different kind of computer than the PyCube, because it runs at a very much higher speed. It's about 2.2 gigahertz. It's a quad core, and so it uses about 15 to 30 watts compared to the PyCube, which might use a few hundred milliwatts. So it's a very, very different computer, but this computer will allow you, for instance, to collect data from a very high capable and very high frame rate camera. In this case, we're using the Unibap IX5 for the high time mission, where we're collecting data at astronomical amounts of data. So it's about 500 megabits per second, if I'm not mistaken. So it's a very, very fast camera. And this computer is also not just a CPU-based computer, but it has a CPU and a GPU, a graphics processing unit, and also an FPGA. So the FPGA will collect the camera data and then send it via the PCI Express lane to the CPU and the GPU for further processing and storage. I just wanted you to be aware of these so you can see the differences in computers that are available out there. Also, the cost of such a computer is much, much higher than the PyCube and other computers that I've shown before. Okay, and now let's talk a little bit about the electronic components that go into these computers. One of the main important components is the memory. So there's various kinds of memory, various kinds of prices and availability. So again, it depends on the mission, but we have one of the common ones is SRAM, then DRAM, dynamic RAM, is also becoming very, very popular in many computer architectures, also like your PCs and things like that. Flash memory is also very, very common nowadays. In fact, flash memory has been around for several years now. MRAM, like the PyCube has, is magnetoresistive RAM. And then we have FRAM, so ferroelectric RAM, and other kinds of RAM. But here's a table that summarizes the properties of these RAMs. And one thing that I'm interested usually is to see the radiation dosage, so the total ionizing dosage. And you can see that flash here is about 30 kilorad. This means flash would survive about a 1 or 2 year mission in low Earth orbit. But if you need more time, or if you're going beyond low Earth orbit, you want to look into different kinds of memory. So in this case, SRAM is 1 million rad, so that's a lot. And it has unlimited endurance. So these are great memory. But the downside of this is that the power is very high. So 500 milliwatts compared to 30 milliwatts. So if you're in a very low budget, low power system, you want something like this rather than that. Again, it depends on your mission. So you can see here the variability. MRAM is actually quite high in terms of power consumption. Yeah, so that gives you an overview of what you can expect. And then there's all these interfaces. So of course, your computer by itself is useless. So you want to communicate with the radio. You want to collect sensor information and things like that. So these are some of the typical electrical interfaces that you can find. RS-232, RS-422, 45. These are serial communication interfaces that are typically available. You have also synchronous serial communication interfaces. So I2C is a very common one. SPI is another very common one. And let's see, I put a picture here of the Raspberry Pi, so you can see some of these. So you have here SPI in pink. I2C is here listed in blue. Then you have the serial communication interfaces like RS-232, or in this case, it's going to be TTL level. You have UART0, TX, and RX. So this is usually where your serial communication is. But there's many others, right? So you have networks like Ethernet, which also the Raspberry Pi has. This is the Internet controller. You have CAN bus. It's a very reliable bus, actually, much more reliable than I2C. So in many missions, we implement CAN buses. And then you have analog to digital and digital to analog interfaces, so that you can read analog sensors and convert them to digital signals. You have debugging ports like JTAG is a very common one. And if you need more high throughput, you can use things like SpaceWire and then LVDS. These are two common ones, but typically for cameras that produce a lot of data, like the high-tech camera. So if you don't need something like that, you don't need to worry about SpaceWire or LVDS, but you know that it exists once you come across a payload that requires a lot of data. Okay, so let's talk about radiation effects and mitigation. So deep space missions or long duration missions, even in low Earth orbit, have to have some kind of radiation mitigation strategy. And CubeSats sometimes don't have to worry too much about these, but it's still good practice because we will face radiation in space no matter what. But the higher or the more critical a mission is, the more important this factor becomes. So space radiation can damage electronics in these two primary ways. One is the accumulation of radiation, or the total ionizing dose. This dose is measured usually in kilorads and degrades the electronics and mostly the transistors. So that is one particular concern that we have to address. And the other one is the single event effects. So these are cosmic radiation that hits or a single particle that hits a piece of electronics, and that creates either a single event of upset, which is non-destructive usually. It just flips a memory part of the computer, or a single event latch up. Latch ups could be more problematic because when a latch up happens, there's a lot of energy, a lot of current that is generated because of a short circuit. And if we don't cut that, it could potentially damage the circuit permanently, and there's no recovery. So let's talk about how we mitigate some of these effects. For memories, we can use FRAM, which is a non-volatile memory. And this can be very useful, especially for storing like the boot process or the boot software for the computer. So in this case, we have this example here. The FRAM is implemented in this chip. So we know that every time the computer boots, it will not alter its boot sequence because it's stored in FRAM. The other memory that can be used is this MRAM, is also a non-volatile random access memory that is persistent. So the PyCube has a type of MRAM implemented in it. In terms of, there are other things we can do in terms of protecting the memory. One type is error correcting code memory. So ECC memory usually is implemented in the memory itself, and it checks for the memory space and computes checksum for that. And if there's any changes to that checksum or to that memory, and the checksum doesn't match from a previous one, then we can go and retrieve possibly a stored area of memory and replace it. This is also similar to the software detection and correction codes that are shown here on the right. And then in terms of protection circuits, we have Watchdog Timers. So Watchdog Timers will monitor a processor or a particular chip on the flight computer. And then if that chip stops responding, the Watchdog Timer will issue a reset so that the whole board will just recover. Usually this happens by a single event upset. Memory state gets corrupted, then the computer program cannot proceed, stops responding, the Watchdog Timer acts, reboots everything, and then everything is fine after that. Another way to protect the circuit is these single event latch up protections. So we can implement something in the circuitry that detects if there's a high current burst that happens and immediately shut down that lane. So if we're quick enough to respond, it's possible to safeguard that circuit and then reset the circuit, and hopefully that latch up has disappeared and everything is fine. Finally, by power controlling devices. So if your spacecraft has multiple subsystems, you don't need them on, it's good practice to turn them off, because the power they consume also is not desired. And also circuits that are turned on, they will be affected by radiation. So if they're not being used, might as well protect them by turning them off. So these are simple practices that can implement safe measures to mitigate radiation effects. So back to our mission. We want to have a big picture of the whole spacecraft, and one of the diagrams that we need to do is this block diagram, like the architecture diagram of your spacecraft. So you want to understand how your onboard computer sits in in context with everything else, right? So your ADCS, your EPS, payload, etc. So I listed here an example for the Neutron 1 mission and also for the Kiao mission. So this is available on the repository on the Google Drive, and you guys can alter these to your needs. And then we have this the block diagram focusing on the OBC itself. We want to adapt this diagram, create a diagram also that represents the exact hardware that you will be using and the functions from the PyCube and the BeagleBone, so that you know exactly how your computer is behaving. And this will help you implement some of these mitigation strategies that we discussed, and also help you understand how everything connects to everything. It's useful for software development, hardware development, etc. So I've listed here some lab work that you guys can do to implement these diagrams. So wrapping up, we have a number of open source hardware platforms that have started to hold promise to fly in space. Of particular interest to us is the BeagleBone. So this has become quite popular. It's a quite popular even among the robotics communities and amateur embedded developers communities. And the BeagleSat is an open source CubeSat platform that uses the BeagleBone. So that's an example of a project using that. And the Pumpkin MBM2 is also using the same processor for space. This is actually a commercially available product. And the PyCube has successfully flown on the KickSat-2 mission and is planned to fly in future missions as well. So both these boards have flight heritage and radiation mitigation strategies. So we're in good hands in terms of continuing our development. Okay, so I've suggested a couple videos for you guys to watch. There's these two videos that help us understand how computers work in space and how they're affected by radiation. So the universe is hostile to computers by Veritasium, and this other talk, Light Years Ahead, that discuss about the Apollo guidance computer. These are very interesting discussions. So with that, I'll leave you to work on the lab and work on the PyCube board and BeagleBone. And if you guys have any questions, you can always reach me out. And thank you for attending the lecture. Talk to you next time.